All right, everybody, we're going to show you how to get it set up for everyone's favorite lab, the flame test lab. You're going to need a ring stand, your utility clamp, your computer, an old Bunsen burner. These are both in the same box for a Spectral, a fiber optic cable that goes into the Spectral, a set of solutions, some water with a piece of wood soaking in it, your sparker, and some sodium chloride. And then we'll show you how to get things set up. Okay, so for the SpectraViz, the default settings are for this to be have a solution put into it, and you would record how much light that solution absorbs. But we need to change the settings because of the fiber optic cable. And you do that by going into the upper left corner here, and you're going to be setting it for intensity. And if you choose to, you can go to graph options and bring back the visible spectrum. Okay, so what you're going to do when this is set up is you're going to hit collect on Logger Pro, and you're going to spray your sample into the flame. You can see the peaks on Logger Pro of the intensity. You can move it a little bit closer so long as you're careful not to spray the sensor or get it into the flame. And you're going to try to stop as the peak is showing up. So even if you miss the highest portion of the peak, as long as you get it there a little bit, what you'll do is you'll go to the examine function on Logger Pro and scroll over until you're at the very top, and it will tell you the wavelength, and you would write that down for that sample. So for instance, I just sprayed in K, potassium, and I got that its wavelength where I had the highest intensity was 770 nanometers. Because I put the spectrum here, it did show that it was in the red area. You don't have to have this spectrum to get this lab. So that's part one, is that you're just going to be spraying single samples so that you get wavelengths for their peak relative intensity. You'll do calcium, sodium, lithium, barium, potassium, strontium. Part two is where you're going to be spraying in mixtures. And so, for example, with this one, this is sodium nitrate and strontium nitrate mixed together in this water dissolved, and you're going to spray them both, and you're going to see hopefully two peaks that correspond to sodium and strontium as they were by themselves. Next, you're going to be looking at if sodium has different wavelengths of color, whether it's in different forms. And so the one that is just labeled as sodium is sodium nitrate. You'll spray in sodium chloride to see if its peak is any different. This is sodium chloride table salt that's dissolved in water. And last, for that, you'll take some solid sodium chloride that's not dissolved, and you will put it onto the tip of the wet splint and put that into the flame and see if it gives you the same color, the same wavelength as the other forms of sodium. And lastly, you have 4 unknowns. You'll spray those in and you'll look at where their peaks are and try to identify what nitrate was dissolved in here. One of the unknowns is a mixture. Hey everybody, we're here. We're going to show you how to do this part of the lab, the flame test. There are 4 parts to it. We're here on the weekend, so the gas isn't working, so we're going to use a propane cylinder. You're going to use your Bunsen burners. For this first part of the lab, there are 4 subparts. In the first part, we're just going to test all of these different solutions. They're different types of salts called nitrates that are dissolved in water. Yep. And so this one, even though it just says Cu for copper, it's actually a copper nitrate, or strontium nitrate, or potassium nitrate. Next, we're going to be testing mixtures. So this one is sodium nitrate mixed with potassium nitrate. We're going to look at them normally as well as through cobalt glass. Cobalt glass is supposed to filter out the yellowish orange of the sodium flame. Next, we'll be looking at different forms of sodium. We'll still use the sodium nitrate. We'll compare it to see if it's the same color as sodium chloride or sodium chloride that's not dissolved in water, which we'll get onto this splint. We'll get it onto there and then put it into the flame. And then last, we'll be testing for unknowns, and we'll see what they most closely resemble of the knowns and mixtures. Okay, first is copper nitrate. Can you see it? What color?
Green and yellow and orange.
Well, let's see. Okay, now strontium nitrate. And now potassium nitrate. And now sodium nitrate. You're not going to do that now.
Why am I not going to do that now?
Because I already did it. Now calcium nitrate. Do not.
Then you do this one?
No. Now lithium nitrate.
Can I do some?
After. At the end you can, okay? And barium nitrate. I'll let you put the piece of wood in when we're ready.
I think we need to put a piece of
Okay.
wood in.
Next are the mixtures. This is sodium nitrate and strontium nitrate. And this is it with the cobalt glass. This is the sodium and potassium nitrate together. And through the cobalt glass. Okay, this is sodium nitrate again. And this is sodium chloride. Different forms of sodium. And this is sodium chloride on a stick. You want to try? Can you reach? Okay. Next is unknown A. And unknown B. Unknown C. Unknown C could be sodium, or it could be a mixture with sodium, so we'll also look at it through the cobalt glass. And unknown D. All right, so there you have it. Hopefully, if people can't make it to class, you're able to see these and it's able to help. Otherwise, maybe you'll just watch it in class and it'll help you figure out what to do or what you're seeing. All right, bye.
Yeah, blah 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 blah.
Say bye.
He does everything because he's a science teacher, and I'm a science teacher too. Okay, bye.
Now I'm going to walk you through some calculations here about part 2 of the lab. What you're going to be doing is using an energy level diagram or Grotrian diagram to predict what colors of light you'll be able to see when you look through a diffraction grating at a gas discharge tube of helium. We're going to use a Grotrian diagram of hydrogen to go through the calculations, and then you'll follow along when you get a Grotrian diagram of helium. Now, what you can see is that with hydrogen, that any time an electron jumps from any shell down to the first shell, the energy is going to be so great that it's in the UV range. And those are all called the Lyman series of lines. And so if an electron were to jump even from the second shell down to the first shell or energy level, the amount of energy would be so great it would be UV light and we could not see it. On the opposite end would be the Paschen, Brackett, and Fund series, and these are all based on where the electron ends. With the Paschen series, all of the jumps are so short because they end at the third energy level. They're so short that the light would be in the infrared range. The Balmer series of lines for a hydrogen atom is where the electron falls from an outer ring and ends at the second ring or second energy level. Still, the one from 7 to 2 is going to be in the UV range, but then we've got 4 lines that we should be able to see. This is a Bohr model-based Grotrian diagram. This one is more accurate. It's a Grotrian diagram that has S, P, D, and F sublevels. But remember that for hydrogen, the sublevels are all at the same level as their principal energy level in terms of energy. And so there is no difference between using this or using this. This is more accurate. This is easier to read and understand. Now notice the transition rules are followed here, where an electron can only move between energy levels by also changing its sublevel. And it changes its sublevel by 1. And so there's never a case where an electron in a p orbital would fall to a different p orbital at a different principal energy level. It has to change its value for L, or its sublevel, or its orbital shape, and it has to change it only by 1. So a p could fall to an S sublevel, a p could fall to a D sublevel, but a p could not fall to a p. Similarly, an S could fall to a p sublevel, but not a D or F. It can only move 1 over in either direction. So the way this is going to work is for each energy jump, we're going to calculate the amount of energy for it. And that would be by finding the difference between the two. These are negatives, which means that if the electron were not associated with the atom, it was considered to have 0 energy. And because it's moving closer and losing energy compared to 0, it has negative energy the closer it gets to the center of the atom. The 3s to 2p, so 3s to 2p, is really the same as the 3 to 2 here, and so we can use either set of numbers. So negative 1.5 to negative 3.4. Final minus initial, keeping the negatives, would give us a value of 1.9 electron volts. And this would be a negative amount of energy. Since the energy is being released as light, we're going to use the absolute value of it. Now to go from energy to wavelength, it's going to be a bit more of a calculation. You're going to be using the equation that relates the speed of light, its energy, and its wavelength using Planck's constant. Where the energy of the photon equals Planck's constant times the speed of light divided by the wavelength. Since we're trying to solve for wavelength, we'll need to rearrange this. And so it would be multiplying both sides by the wavelength and then dividing both sides by the energy of the photon. Really, these two variables are going to be switching. And so again, the energy is the amount of energy that that photon, that wave of light, would be giving off. C is the speed of light, which is 3.00 times 10 to the 17th nanometers per second. And H is Planck's constant, which is 4.136 times 10 to the negative 15th electron volts per second. And we get for this 653 nanometers for this size jump. The color that would be, you would look on a reference sheet for the spectrum of color in the visible spectrum, where it compares nanometers to the visible color that you would call it. If you did that, you would find that 653 nanometers is going to be red. To figure out the number of degrees that this band of color is going to be shifted, you're going to use the Bragg equation. The Bragg equation is that d, which is the distance between ridges in the diffraction grating. And so each diffraction grating, each piece of plastic, has a certain distance between its ridges. The ones that you all are going to be using this year have this distance between each ridge, 1,400 nanometers. And so that is what d would be. Sine theta means sine of the angle that is going to be bent equals the wavelength. We're going to have to rearrange that a little bit. And so by the angle theta, what we're referring to would be that you have your light source. It's not going to look like a bulb, but more like a skinny tube, and it's going to be giving off light. You're going to have a meter stick that is coming down. So this is if you were looking at a bird's eye view. And perpendicular to it, you will have another meter stick. You're going to look at the diffraction grating from 80 centimeters back. You're going to see the light, but you're also going to see some different bands of different colors. And so you are going to see, and you're going to look through, and this angle is the one to which we are referring, theta. So you know that this distance is 80 centimeters. You're trying to predict what this distance will be for this one band that we're calculating right now, this red band. So when you look through the diffraction grating, what angle will it be? And how far away from the light will it be is what we're ultimately calculating. So now we're doing, as an intermediate step, the angle. The Bragg equation is typically used in this way, where the distance between the bands on the diffraction grating. Remember, diffraction grating is plastic with little ridges. The distance between ridges on the diffraction grating times the sine of the angle created by the perpendicular and where the band shows up is equal to the wavelength of light. And so what we're going to do is plug in 653 1,400 nanometers and sine theta. The way to solve for this is divide both sides by 1,400. And then you would have this, and you would take the inverse sine to get the angle theta. When I show you how to do all of these more quickly on Google Slides, when I show you how to do these more quickly using Google Spreadsheets, instead of sine -1, it's going to be a sine, or ASIN, and then in parentheses the number that you're trying to work with. So this will give you an angle. In Google Sheets, it'll be in radians, and I'll show you how to switch that when I do the Google Sheets. So now we have an angle for this. And finally, we're going to be looking for the distance. We know the side and we know the angle, and that will let us solve for this, because this distance divided by this distance is the tangent of this, 19.1. And so it's going to be 80, which is the distance back that you would hold your diffraction grating, times the tangent of the angle, equals that opposite side, or how far away from the light source that red band will be. So what you're going to be doing now, so what I'm going to do now is I'm going to put these same equations into a spreadsheet on Google and show you how to calculate all of these just using this, and then using the formulas to fill in this, this, and this. Those will give you some predictions once you look at a growth train diagram for helium of where those lines should appear. And you're going to put markers down on the meter stick and look through the diffraction grating and see if your lines match up to where you put your predictions, your markers. And the whole point of this is to prove, to confirm that this works. And so you'll find that you are very, very close, if not right on. All right, now that you've got your predictions made, we're going to show you how this works with hydrogen, just like the examples. You're going to do this with helium and try to predict where the 7 lines for helium are going to be. We're only going to predict for the 4 lines of hydrogen. We'll show you how that works out. You've got the equipment here. A lot of this is actually going to be set up for you, and you're just going to come make your predictions at the station and then test it and leave. All right, so you're going to use these little paper clips with one part bent up. You're going to put them on the meter stick where you think the lines are going to be. You should use this side, and you're going to be holding the diffraction grating up at exactly the 80 centimeter mark and looking through to see where the lines fall. So we made our predictions before that away from the midpoint, they should be 16.2, 16.8, 17.8, 20.1, and 27.7 centimeters away from the midpoint. You're going to have to do a little bit of math because the midpoint is 50, and so you're going to have to calculate out. Right, once you get them set up in your predicted distances, you're going to shut down the lights. You're going to take the diffraction grating, hold it at 80 centimeters, and look through to see how you did. So let's take this off of here. So this is at 80 centimeters. And the places predicted were here, 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 and here.